Chapter 12. Analysis of Variance. A group of procedures known as analysis of variance, ANOVA, was introduced in this chapter. The procedures presented here represent a wide range of techniques used to determine whether three or more populations have equal means. Depending upon the experimental design employed, there are different hypothesis tests that must be performed. The one-way design is used to test whether three or more populations have equal mean values when the samples from the populations are considered to be independent. If an outside source of variation is present, the randomized complete block design is used. If there are two factors of interest and we wish to test to see whether the levels of each separate factor have equal means, then a two-factor design with replications is used. Regardless of which method is used, if the null hypothesis of equal means is rejected, methods presented in this chapter enable you to determine which pairs of populations have different means. Analysis of variance is actually an array of statistical techniques used to test hypotheses related to these, and many other, experimental designs. By completing this chapter, you have been introduced to some of the most popular ANOVA techniques. One-way analysis of variance. There are often circumstances in which independent samples are obtained from two or more levels of a single factor to determine if the levels have equal means. The experimental design which produces the data for this experiment is referred to as a completely randomized design. The appropriate statistical tool for conducting the hypothesis test related to this experimental design is analysis of variance. Because this procedure addresses an experiment with only one factor, it is called a one-way analysis of variance. The concept acknowledges that the data produced by the completely randomized design will not all be the same value. This indicates that there is variation in the data. This is referred to as the total variation. Each level's data exhibits dispersion as well and is called the within-sample variation. The dispersion between the factor levels is designated as the between-sample variation. The ratio between estimators of these two variances forms the test statistic used to detect differences in the level's means. If the null hypothesis of equal means is rejected, the Tukey-Kramer procedure was presented to determine which pairs of populations have different means. Randomized complete block analysis of variance. Section 1 addressed procedures for determining the equality of three or more population means of the levels of a single factor. In this case, all other unknown sources of variation are addressed by the use of randomization. However, there are situations in which an additional known factor with at least two levels is impinging on the response variable of interest. A technique called blocking is used in such cases to eliminate the effects of the levels of the additional known factor on the analysis of variance. As was the case in section 12.1, a multiple comparisons procedure known as Fisher's least significant difference can be used to determine any difference among the population means of a randomized block ANOVA design. Two-factor analysis of variance with replication. Two-factor ANOVA follows the same logic as was the case in the one-way and complete block ANOVA designs. In the latter two procedures, there is only one factor of interest. In the two-factor ANOVA, there are two factors of interest. Each factor of interest introduces variability into the experiment. There are circumstances in which the presence of a level of one factor affects the relationship between the response variable and the levels of the other factor. This effect is called interaction and, if present, is another source of variation. As was the case in sections 1 and 2, we must find estimators for each source of variation. Identifying the appropriate sums of squares and then dividing each by its degrees of freedom does this. If the variation accounted for by factor A, factor B, and interaction is large relative to the error variation, we will tend to conclude that the factor levels have different means. The technique that is used when we wish to analyze two factors as described above is called two-factor ANOVA with replication. Conclusion. Chapter 12 has illustrated there are many instances in business in which we are interested in testing to determine whether three or more populations have equal means. The technique for performing such tests is called analysis of variance. If the sample means tend to be substantially different, then the hypothesis of equal means is rejected. The most elementary ANOVA experimental design is the one-way design, which is used to test whether three or more populations have equal mean values when the samples from the populations are considered to be independent. If we need to control for an outside source of variation, analogous to forming paired samples in Chapter 11, we can use the randomized complete block design. If there are two factors of interest and we wish to test to see whether the levels of each separate factor have equal means,